The Earth sits at just the right distance from the Sun, about 93 million miles, a seemingly arbitrary number, yet crucial for life as we know it. The Moon, our nearest celestial neighbor, is approximately 238,000 miles away. These distances aren't just random. They form the intricate web of conditions necessary for life on our planet. That Earth's orbit around the Sun places it in the habitable zone, a narrow band where temperatures are just right for liquid water, a vital ingredient for life. Even minor changes in this distance could have dramatically different results. If Earth were just 5% closer to the Sun, it might become so hot that oceans would evaporate, turning our world into a barren desert. On the other hand, if Earth were 5% farther away, it could be too cold, freezing over and preventing the existence of liquid water. The Moon's gravitational pull plays a crucial role in stabilizing Earth's axial tilt, which in turn governs our climate and seasons. This delicate balance creates a stable environment where life can flourish. If the Moon were significantly farther away, its gravitational influence would weaken, leading to a chaotic climate with extreme seasonal changes, making it difficult for life to thrive. 400 million miles away, Jupiter plays the role of Earth's protector. With its massive gravitational field, Jupiter captures or deflects many comets and asteroids that might otherwise strike Earth. Without Jupiter, the inner solar system, including Earth, would face constant bombardment from space debris, leading to frequent and catastrophic impacts that could disrupt the evolution of life. Our solar system's position within the Milky Way is another stroke of cosmic luck. We reside in a relatively calm and stable region, far from the galaxy's turbulent center, where supernovae and black holes dominate. This positioning shields us from excessive cosmic radiation and gravitational disturbances, allowing the solar system to maintain its structure. On an even grander scale, the universe itself operates on finely tuned constants and physical laws. Take gravity, for example. If the force of gravity were slightly stronger, stars would burn through their fuel much more quickly, leaving little time for planetary systems to form. Conversely, if gravity were weaker, matter might not clump together to form stars and galaxies at all, leaving the universe dark and lifeless. Even the masses of subatomic particles, like protons and neutrons, are precisely set. A slight change in the proton's mass could disrupt the delicate balance within atomic nuclei, destabilizing atoms themselves. If protons were much heavier, they might decay rapidly, leading to the collapse of matter as we know it. On the other hand, if neutrons were lighter, atomic nuclei wouldn't hold together, preventing the formation of elements essential for life. These constants and laws, seemingly plucked from a cosmic menu, are all set at values that allow galaxies, stars, and planets to form. If any of these values were even slightly different, the universe could be a vastly different place. One where galaxies, stars, and planets as we know them might not exist, and life would be impossible. So, how did this incredible balance come to be? What is the origin of these precise configurations that shape the solar system, the galaxy, and the entire universe? Are these perfect conditions the result of random chance, a fundamental necessity, or something more profound? Could such fine-tuning be mere coincidence, or does it hint at a deeper order within the cosmos? 13.8 billion years ago, the universe began with an almost unimaginably tiny point, a singularity. To grasp its scale, imagine a speck of dust, then shrink it until it's a billion times smaller. Even that wouldn't compare to the singularity's size. Yet within this minuscule point existed all the energy, matter, and potential of the entire cosmos. The singularity was not only tiny, but also incredibly hot and dense, with temperatures reaching trillions of degrees. At such extreme heat, atoms couldn't form. Even protons and neutrons were melted into a hot, dense soup of fundamental particles and energy. The density was so great that the very fabric of space and time was curved to an infinite degree. This tiny, incredibly hot and dense point was the beginning of everything, containing within it the seeds of all galaxies, stars, planets, and life itself. But it was also highly unstable, and in an instant, this instability triggered the expansion we now call the Big Bang. The Big Bang was an explosion in space, but an explosion of space itself. The universe rapidly expanded from this initial point, taking with it the primordial particles and energy. This was the beginning, but it was only the first chapter in the story of the cosmos. Immediately after the Big Bang, the universe underwent an extraordinary phase of growth known as cosmic inflation. This inflation happened in a fraction of a second, but had profound effects. It smoothed out any initial clumps or irregularities, resulting in the uniform cosmos we observe today. This smoothing effect was incredibly precise. Had the expansion rate deviated even slightly, the consequences would have been catastrophic. A slower rate might have caused the universe to collapse back on itself, while a faster rate could have spread matter so thinly that galaxies, stars, and planets would never have formed. As the universe continued to expand, the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, began to differentiate. The strengths of these forces had to be just right for the universe to evolve as it did. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together, and atoms wouldn't exist. If it were slightly stronger, stars would burn out too quickly, preventing the long-term stability needed for life to develop. During the early stages of the universe, fundamental particles like quarks and electrons began to form. These particles combined to create protons and neutrons, which then fused to form the first atomic nuclei in a process known as nucleosynthesis. The ratio of protons to neutrons was crucial. Any significant imbalance could have resulted in a universe dominated by either hydrogen or helium, preventing the formation of heavier elements essential for life. As the universe continued to cool and expand, it reached a critical point known as recombination, where protons and electrons combined to form neutral hydrogen atoms. This process allowed light to travel freely, leading to the release of the cosmic microwave background radiation, which we can still observe today. The timing of recombination was vital. Had it occurred too early or too late, the distribution of matter and radiation would have been drastically different, potentially disrupting the formation of galaxies and stars. Following recombination, the universe entered a period known as the Dark Ages, lasting until about 150 million to 1 billion years after the Big Bang. During this time, there were no stars or galaxies, only neutral hydrogen. The rate of cooling and initial density fluctuations, remnants of inflation, were finally balanced to allow gravity to amplify these fluctuations, eventually leading to the formation of the first stars and galaxies. As the first stars ignited, their ultraviolet light ionized the surrounding hydrogen gas, marking the beginning of the era of reionization. The timing and intensity of this process were critical in shaping the development of large-scale structures like galaxies and galaxy clusters. Dark matter, an invisible form of matter that does not emit light or energy, played a significant role during this period. Its gravitational forces acted as scaffolding for visible matter, allowing galaxies and larger structures to form. Without dark matter, the universe's structure would be vastly different. Dark energy, another mysterious component of the cosmos, began influencing the universe's expansion in its later stages. This force drives the accelerated expansion of the universe, and its balance with dark matter is yet another example of fine-tuning. If dark energy were stronger or weaker, it could have prevented galaxies from forming or caused the universe to expand too rapidly for structures to hold together. The universe's journey continued with the formation of the first stars and galaxies, a period known as the Cosmic Dawn. The precise tuning of gravity allowed these stars to form. If gravity were slightly weaker, matter wouldn't have clumped together, and stars wouldn't have ignited. If it were stronger, the universe might have collapsed before stars could form. These first stars eventually underwent supernova explosions, spreading heavier elements throughout the universe, elements essential for the formation of planets and, ultimately, life. The formation of galaxies required a fine balance of gravitational forces and the universe's expansion rate. Hubble's law, which describes the rate at which galaxies move apart, plays a crucial role in understanding this balance. Galaxy clusters, large groupings of galaxies, formed under specific conditions. The universe's cooling, density fluctuations, and the influence of dark matter all contributed to the formation of these clusters. Our local group of galaxies, including the Milky Way, is a product of this finely tuned process. Within the Milky Way, our solar system formed under very particular conditions. The sun's stability, the presence of water, and the role of the moon in stabilizing Earth's tilt all contributed to making Earth a habitable planet. The emergence of life on Earth depended on a precise set of conditions: liquid water, the right chemical elements, and a stable climate. From single-celled organisms to complex multicellular life, the evolution of life involved processes only possible in a finely balanced environment. The questions surrounding the universe's fine-tuning are profound. Why do stars burn at the perfect rate? Why do atoms form the way they do? Why didn't the cosmos collapse in on itself shortly after the Big Bang? These are some of the questions that lead to the intriguing concept of the universe being finely tuned. The idea of fine-tuning suggests that the fundamental constants and quantities in the universe are precisely set in such a way that life can exist. Think of it as tuning a radio. You need to get the dial exactly right to catch the station. If you're even slightly off, all you get is static. Similarly, if the universe's parameters were even slightly different, life as we know it wouldn't be possible. This concept of fine-tuning began gaining traction in the mid-20th century, particularly through the work of physicist Fred Hoyle. In the 1950s, Hoyle studied how carbon, a critical element for life, is formed in stars. He discovered that the production of carbon relies on a very specific resonance level within the carbon nucleus. If this resonance level were just a bit different, carbon wouldn't form, and life wouldn't exist. Hoyle famously remarked that it seemed as though the universe was a put-up job, suggesting that the cosmos appears to be designed with life in mind. Since Hoyle's discovery, scientists have identified numerous other examples of fine-tuning. For instance, the strengths of the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are delicately balanced. If gravity were just a tiny bit stronger, stars would burn out too quickly, leaving insufficient time for life to develop. If gravity were weaker, stars might never ignite at all, resulting in a dark, lifeless universe. The electromagnetic force, which governs the chemistry of atoms and molecules, also has to be precisely tuned. If this force were slightly different, atoms wouldn't bond properly, and complex molecules essential for life wouldn't form. The fine-tuning extends to the very beginnings of the universe. The Big Bang, the event that brought the universe into existence, had to be incredibly precise. The density of the universe at that moment had to be balanced to 1 part in 10 to the power of 60. To put that into perspective, it's like having a ruler stretched across the entire observable universe, divided into inch increments, and the initial density of the universe had to be correct within just 1 inch. If it were off by even that minuscule amount, the universe would either have collapsed back on itself or expanded too rapidly for galaxies, stars, and planets to form. One of the most astonishing examples of fine-tuning involves the cosmological constant, which drives the accelerated expansion of the universe. The value of this constant is extraordinarily small, yet it's precisely what's needed for the universe to develop as it has. If the cosmological constant were much larger, the universe would have expanded too quickly for galaxies to form. If it were negative, the universe would have collapsed back into a singularity. The cosmological constant's value is fine-tuned to about 1 part in 10 to the power of 120, a level of precision that is almost unimaginable to us. Oh, why is the universe so perfectly configured to support life? One explanation is the anthropic principle, which states that we observe the universe to be fine-tuned because, if it weren't, we wouldn't be here to observe it. In other words, the universe must have the properties necessary for life because we exist to notice them. This idea first began to take shape in the mid-20th century as physicists and cosmologists grappled with the puzzling observations of how finely tuned various fundamental constants and quantities in the universe seem to be. One of the key figures in developing the anthropic principle was physicist Robert Dicke. In the 1960s, Dicke argued that the conditions we observe in the universe must be compatible with the existence of observers, us. Brandon Carter, a British physicist, formalized this line of thinking in 1973 when he introduced the anthropic principle during a conference celebrating Copernicus's 500th birthday. Carter proposed 2 forms of the principle: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle suggests that the universe's laws and constants appear fine-tuned for life simply because, if they weren't, we wouldn't be here to notice them. This principle is largely observational and doesn't imply anything beyond the fact that we exist in a universe that allows for our existence. The strong anthropic principle, on the other hand, goes a step further. It suggests that the universe must have properties that allow life to develop at some stage in its history. This principle raises profound questions about the nature of the universe and our place within it. Is the universe's fine-tuning the result of sheer coincidence, or does it point to something more? Could there be countless other universes with different physical constants, most of them inhospitable to life, with ours being just one of the rare ones that got the combination right? This idea, known as the multiverse theory, proposes that our universe is just one of many, each with its own set of physical laws and constants. Alternatively, some suggest that the universe's fine-tuning could imply the existence of a deeper, underlying order or design. This idea has led to much debate among scientists, philosophers, and theologians, each offering different interpretations of the evidence. Whether by chance, necessity, or design, the universe's perfect balance is a remarkable phenomenon. It's a delicate harmony of forces, constants, and conditions that have allowed stars to burn, planets to form, and life to emerge. As we continue to explore the cosmos, we may one day uncover the true nature of this fine-tuning, whether it's a cosmic coincidence or the key to understanding the very fabric of our reality.